Okay, we're back. Last time I started trying to make the permutation multiplication stuff, but it turned out that I needed to deal with a bunch of other stuff first. So now we're going to keep working on it. Okay, well, since I last worked on it, I started thinking that the way I did stuff over here was a little bit bizarre. Converting two strings into a permutation at once doesn't really make sense. Also, I only tested single cycle permutations. I never tested stuff, if I had something like this, for example. And I also started thinking that, permutation multiplication and applying a permutation to an element of the set should be good candidates for operator overloading. So we're going to finish up some of this cleanup to make these. One other idea that I had, which we'll get into later, notice here that I intentionally pushed the size of the data vector to the end of the cycles vector, because then it let me make a cleaner for loop. Well, I started thinking that actually every single for loop that's going to deal with these permutations is going to need that same thing. So I'm actually thinking of always putting that at the end of the cycles vector. Okay, so I've briefly mentioned the stuff that we're going to do today, so I guess I'm going to get to work and do it. First thing I want to do is get rid of this pair fill map thingamajig. That just doesn't make sense. Instead, I'm going to make it a constructor. Now, another idea that I had was sometimes you want more than one permutation to be initialized with the same namespace. That's what I'm calling it, as in the map between strings and the integers used internally. So we're also going to have a constructor which takes in another permutation. Well, maybe I'll just take in one of these name maps. And then, so here, what it will do is it will set names to n, but then we're going to have to take the logic of converting the string representation to our internal representation. So let's start by pasting all of this in and taking away the parts that we don't need anymore. So we don't need perm2, that's ridiculous. Something's gotten messed up with the curly braces. Now we're not actually returning anything anymore. And we no longer, we already did that over here, setting the namespace to the input namespace. We only need to copy one string. Oh, fascinating. The namespace itself should keep track of the next ID. Okay, I think we're going to have to make that a separate object, but we can do that in a really nice way, you'll see. So I'll call this an nmap to be consistent, but I just won't have it here anymore. You'll see, it'll make sense. You know what? We could actually call this n, as in n the number of elements in the set, because that's what this number will represent, which will start off. Well, okay, so we need a constructor for this. So the default constructor is, I'm tired of typing that out, so using map type just like that. I'm going to comment this out just to see if what I wrote in here compiles. Okay, that's good. And that should be okay. Like, I think we just need, oh yeah, there we go. Oh, actually, we can do something kind of cool here. No, never mind. I was thinking of being really tricky and overloading the operator. Well, maybe, yeah, we could do this. No, but what did I actually use, though? I don't remember. Yeah, this is going to become n now, but it's actually going to be .n. Oh boy. Okay, no, let's not get into that just yet. Let's just finish this up. Well, actually, I think that is done. Thinking. So now that this has a default constructor, where it will make a new map. We need to be able to insert. Yes. That's, so this is just going to be a wrapper function. I hate writing them. I think you can do something like this. No, I don't think I'm going to find it like that. Because I know that if you inherit from a type, you can do using, and then, you know, some method from that type. Like if you inherited from vector, you could do using vector size. But we're not inheriting, so I don't think we can do that. So instead we're going to have to, I think actually we could do this. We can be really lazy about it. Oh, don't we need forwarding for this? listening to. Oh yeah, I thought it sounded familiar. So this function inserts the string s into the namespace, possibly assigning a new number. Returns the internal number of that string. I don't know if I need to return it, but I may as well. So I think I should be able to actually steal some of the code I wrote over here. I'm just wondering what this insert does if I give it a key that already exists but with a new value of n. Okay, yeah, I think we're okay. Well, it was working before, so. And then here we do n++. And we return it arrow second. Oh yeah, it is still an arrow. Okay, so we have a bunch of errors from the other functions, but that's okay. We can deal with that. I'm tempted to maintain the inverse lookup inside this struct, but that's not really mission critical. We don't have to do that right now. Okay, I think we're ready to move on to this string constructor for the perm class. Also, I was thinking that it would be nice if spaces were also treated as delimiters. You know, I think it would be a lot better if I just did and then I don't have to worry about it. And we had a bug last time where it didn't update them all and I had a problem. Okay, we'll deal with that in a minute. Okay. Okay. So now I think we just do Oh yeah, check this out. So int val is equal to names dot insert toke or talk, and we don't need to do this anymore. We do need to do that, and one more thing is now we're going to do cycles dot pushback pause. So this pushes the size of data to the end of cycles, to the end of cycles, not sucles, in order to simplify iteration. And yeah, I'm sure I'll remember what that means, right? I don't need to return anything. Oh yeah, obviously I need to do data.pushback val. Yeah, we're not using that anymore. Okay, that should be all right. I'd like to test it. The neat thing is that this is the exact same code in both. And actually, we can use delegating constructors for this. I've never used them before, but this is exciting. I think you can just do this. Yeah. Wait. Yeah, well, let's see if it compiles. Oh boy. Yeah, I noticed that since factoid delegation follows mem initializer. Let's just read what that means. I think I understand, but I'm not positive. In the meantime, I think I know how to fix this. So we're going to take this back out, put it back in here. Get rid of this. And then here, we're just going to do like that. Still not quite. Yeah. Okay. Let's read what the error says. Oh. That's odd. Yeah, obviously. Can I... Oh, weird. Oh no. Wait a minute. This integer has to be part of the memory shared. Does that make sense? I hope it makes sense. I don't know how to explain it better than that. Oh, but that's so ugly. Well, I guess I could just have two shared pointers. I mean, what's the harm? It seems a bit ridiculous, though. Or I could go back to having a shared pointer in the perm class as opposed to wrapping it inside another class. Okay, I've decided. I'm going to do it like I had before, a shared pointer inside the perm class. Well, I guess I should use... I really wish my IDE had syntax highlighting for these using definitions. It doesn't always work with typedef. Oh, it seems to work there. And the only difference here is that in the perm class, instead of an nmap, I have a shared pointer to an nmap. Arrow. Wait, no, not arrow. What am I talking about? Wait, I should have read the error. Arrow. Yeah. Okay, I think we're okay. Now let's fix this function here. A perm contains a pointer to an end map called names. Arrow. Right? We're getting there. Yes. Okay, we're almost there. We can just do this. But we'd like them to have the same namespace. So like that, maybe. Okay. I'm glad that compiled. I'm glad that compiled. We have an extra right bracket, which we shouldn't have. That's kind of funny. Let's see if I can fix that. Oh yeah, we don't need this anymore. What am I listening to now? That's pretty good. I know you can't hear it, by the way. Okay, that seems to have fixed it, possibly. Let's just double check. A, C, H, E, D, B, D, E, B, C, D, E. I think we're okay. Is that all I wanted to do? I also want to write the multiplication function, obviously, but I think that's all I need for now. Permutations can only be multiplied if they are in the same namespace. First, let's see if shared pointer has a comparison operator. That should be false. That is true. That's default constructed. So false. Okay, I think we're good. So we can use that. I'm not sure. C++ has this notion of exceptions. I've never liked exceptions. So first thing we do is say if names does not equal other dot names. I don't know, maybe we'll just return this. It'll make a copy. So now we need to do that algorithm. I need to use the iota, I don't know how a Greek person would say it, iota function. So unfortunately I wasn't smart enough to save that diagram I had last time. Maybe I should do it again. I'd really rather not. Well, okay, I can do it in a smarter way though. I don't have to use Paint, I can just use Notepad, because I don't need to be pointing to stuff anymore, I can just look at it for reference. So the permutations at play here are A, C, H, E, D, B. Actually, I have a better idea. I'll already write them like this. D, C, B. So I'm going backwards through them like that. Can't read that. E, D, B, D, H, C, A. Okay. Oh yeah, I guess I need this. So first we start out with everything in its place. I'm going to put the F, I don't really care. So here what we're doing for if it's the right parenthesis, we do nothing. If it's not the right parenthesis, we go to the location indexed by, oh, just realized that's really small. We go to the location indexed by the, you know, the thing in the permutation, the number, I guess. We go to that location and replace it with the next character in the permutation. So that's what that is. So here we will go to D and replace, as in we will go to D, which is in this location, and replace with E. And I think you see the point. And now the trick, when we get to the left parenthesis, we go to the location of the right parenthesis and replace with the character before it. So we have A, C, D, E, B, F, G, H. And last time I spent like, I don't know, at least 5 minutes, probably more than that, wondering what I was doing wrong. Actually, I was doing nothing wrong. This is the correct algorithm. This string here, I mean, we'd have to do the rest of it, but this string here is not. What happens when you take the unpermuted string and permute it? That's not what it means. If I were to apply this permutation to this string, I would have B here, B going to C. I would have C here, C going to D. I would have D here, D goes to E. And I would have E here, E goes to B. But that is not what this means. What this means is it's for each of the inputs where it needs to go. So A goes to A, B goes to C, C goes to D, D goes to E, E goes to B, and the rest are the same. That's exactly what this means. Okay, I hope that makes sense. What we'll have to do is write a function which takes this table and converts it back into the regular cycle notation that we're used to. So I'll do a few more iterations here. I'll just do the DE iteration to, give you the idea. So we don't change anything when we see a right parenthesis. Whoop. No, careful now. This means, wait, I thought it meant go to, here I'm using letters, but really what this means is it's the location, as in the index E, is in this location, I'm pretty sure. We'll double check it and see if that's right. So we have this. Now we go to where D would normally be, right? A, B, C, D. Definitely doesn't seem right. Oh, fascinating. I think that means we actually go to where the E is. That makes the algorithm much less efficient. Much, much, much less efficient. I can't believe that's the way it is. Okay, well, let's do it the way that I think it should be, now that I think I know better. And this D becomes an E, and then this becomes the D. So, under the permutation E, D, B, C, D, E, let's multiply this out by hand. We have E goes to D, goes back to E. D goes to E. Or, I should start at B actually, because that's the way these are usually written. B goes to C. C goes to D. Now D goes to E, goes to B. And then E doesn't move. So apparently this is the permutation that we should have. B, C, D. B goes to C. C goes to E. Uh-oh. That's not right. It should be D. And E goes to B is definitely not right. Does Donald Knuth multiply his permutations right to left? Let's do that. I always do them left to right, okay? That's my doing it, but let's, so here we have B goes to C as usual, C goes to D, but then D goes to E. Oh yeah, look at that. C, right, C goes to D, D goes to E. Then E goes to B. So Donald-Knuth multiplies his permutations right to left. I guess we can live with that. I'm thinking. I'm still thinking. Also, this algorithm is not that nice because you have to do a linear search. Alright, I'm pulling out the book. I'm going to take a look and see if I missed something because this algorithm is supposed to be pretty good. Oh no, he does it the way that I was just doing it. Alright. I think I made a mistake. Also, I was pretty sure that Donald-Knuth multiplied his permutations left to right. Usually computer scientists do stuff in the way which is more immediately intuitive when it comes to mathematics. It's only mathematicians who do stuff in a weird way. Okay, let's get rid of these and try it again. A, B, C, D, E. Ah, yes. So last time I was saying to myself that you have to store the one which was overwritten. Oh, okay, I see. I get it. Here, this doesn't mean replace it with an E. Oh, sorry. Yeah, this doesn't mean replace it with an E. Wait. Shoot. Let me think about this. A, B, C, D. So what do we replace here? With the B, obviously, right? It means replace it with the thing at location E. That doesn't replace it with an E. Replace it with the thing at location E. A, B, C, D, E, right? With the B. That makes sense. And then here, A, B, C, D, E. And this means replace it with the thing in location D, like that. So these indices are referring, okay, so when we see a right parenthesis, we save a copy of this, I think. Okay, this algorithm is still good. We're okay. This means go to location E and replace it with the item in the copy indexed by the item before it. Now in this case, the item before it is the right bracket, so we put in the special right bracket symbol here. Here, this means go to location D and replace it with the thing in the copy at location E with the B. And then here when we get to the left parenthesis, it means go to where the right parenthesis is and replace it with the thing in location D. That happens to be an E. Okay, got that? Yeah, I'm not 100%, not 100% sure why this works. I mean, I kind of have a feeling I know why, because you take the thing in location E and it's going to go to the thing in location parenthesis. We don't know what it is yet because we haven't read that far down. You take the thing in location D, replace it with the thing in location E. It all makes sense. The thing in location C, replace it with the thing in location D. And by the way, this is the permutation BCD, which is exactly what we expect. Oh, you know what? We don't have to copy it. So here we don't copy it at all. Here what we're going to have is we're going to save a temporary. We're going to shuffle the temporary along. So here we don't have anything in the temporary. Here the temporary is whatever was overwritten. Here the temporary is whatever was overwritten. And now we don't even have to search the location. As in, here we went to location E and overwrote what was there. But here we're going to go to location D and overwrite with what was in location E. Well, that's the thing we just overwrote. So we save the thing that we just overwrote. And that's what we copy in. We don't even have to do a second index into the array. Yeah, this is much, 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 much more like it. Right? So here, we went to location C. So the thing that we overwrote was a C. Here we go to location B, put the thing that we saved in it at location B, and then hold on to the thing that we just overwrote. This is much nicer. Then here we go to the, here we go to the right bracket and replace with the temporary, which was B. And then here, there's nothing to do. Actually, the thing I accidentally just typed is a perfect symbol to mean null. So I'm going to use it. I'm using the Canadian multilingual standard keyword, and you got that by doing right control O. Okay, so here it's a B. Here we go to location D, replace with the B, the thing that we replaced was an E. And then here we, oh yeah, perfect. This is making sense. You know what, I'm just gonna not write anything. I find it's too confusing. Okay, so now let's do it with our new method. We go to location B, save what's there, and replace with, well, in this case, there's nothing left in you know what? We immediately set temporary to right parenthesis when we encounter it. So that's going to be the rule. So we go to location B and put in whatever was in the temporary. Here we go to location D, A, B, C, D, replace it with what's in the temporary, but we save the temporary, which would be, so we do a swap basically. we swap the temporary with the location. So A, B, C, D, E. So swap the B and E. A, B, C, D, E, F, G, H. A, B, C. Yeah. We're done. So the final permutation we have, is A goes to D, right? That's what this means. A goes to D. D goes to C. C goes to H. H goes to E. E goes to B. B goes to A. And F and G don't move. Well, that's not surprising because we never had them in the first place. I don't know why I'm bothering to delete them, but... So after we're done writing our permutation multiplication function, and of course the table reduction function, which we just sort of did in our heads, this is what we should get, add Cheb. Okay. Okay, so now that we're really clear on how it works, we're gonna have a vector of int. I don't know what to call this guy. You know, this temporary save or whatever. I guess state or current. Current seems good. And its size is going to be equal to this is a numeric. Now we can run the algorithm. Starting at other, we travel backwards. Yes. You know what? Since we have to return a permutation, we should write ourselves, I'm not going to do it yet, I'll finish writing the multiplication function first. We should write ourselves a constructor taking in a vector of int. And I just made this a const ref, but usually, surprisingly, it's better to not even bother with that. Okay. Now, let's do this. So starting at yes, so this is where the cycles vector is going to come into play. The cycles vector is going to tell us where these right and left brackets are. So we have to be a little bit more careful. So here we start at Oh, fascinating. We can do this. Also, it's really annoying, this warning. I wish I could turn off this particular warning. There's probably a way, I just don't know how to do it. So here, the permutation B, C, D, E, well, no, A, C, H, E, D, B, D, E would actually be stored as C, H, E, D, E, and with cycles at 0, it's always 0. 1, 2, 3, 4, 5, and 7. So that's what we have, data equals and cycles. So we need a temp. So I guess I am going to end up using -1 to mean the right parenthesis. I don't think anybody's going to have, 4.2 billion different names in their permutations. Yeah. So we could even be clever about it and do and what time is it? It's getting late. By the way, I don't want to do a linear search to find this r paren when we encounter the left paren. So we can just cache it since we're going to have to do it anyway. So int whole index, I don't know what else to call it. You know what? We do this for each cycle. Equal to and we can just do whatever for temp, although we may as well make it -1. It doesn't actually matter. It doesn't matter what we put in here because it'll eventually get overridden with something meaningful. So actually, you can have 4.2 billion names if you want. Okay. Now, do we want greater than or greater than or equal? Oh, yeah, -1, -1. Oh, -2. Because now that we don't actually encounter the right parentheses, this step doesn't exist. It's sort of like an init step, actually. As in, it's this stuff, right? We do this for each cycle. For each cycle. so we can have some init stuff before we do it. So this is the init. So I'll just label that as the lowercase I. And thinking. Why don't we, for the init, just make temp equal to whatever was in the location of, you know, this first iteration, and move immediately to the second iteration. Because here, if this is still E, it doesn't matter, because it's eventually going to get overwritten down here. I'll leave it as a right bracket for now. So for our init, we really just need to do this. And then, you know, we're golden. And this will stay as E's. I'm not even going to change that. Then here we don't have this step. That's just the termination condition. J is greater than or equal to other dot cycles I minus 1. Okay, yeah, other dot cycles I minus 1. Wait, no. Wait. It's data. It's other. Oh, this is confusing. Very confusing. Okay, let's initialize J right here. J is equal to other dot cycles of I. So here there is no 7, right? 0, 1, 2, 3, 4, 5, 6, 7. Oh, wait a minute. But there isn't supposed to be. Wait, hold on. 0, location of the first cycle. 1, 2, 3, 4, 5. Oh, the location of the second cycle is 6. Not 7. Or not 5. And then 8. 6, and then 8. So we need to go here to J is equal to other cycles I minus 1. Here we're going to do greater than 0. So we can save this whole index in J like this. Then here we do, yeah, I minus 1 and J minus. And here it's very, very simple. Is it? Yeah. Oh yeah. We need. Wait. So as part of the initialization, we need to grab the element of that location. So we can't use our paren. This is other.data at J, and the whole index is equal to J. Then here what we do is we just simply swap other data. I think we can just use standard swap for this. Maybe other data at J and temp. In fact, we can even go on one line like that. And then we just do the same thing. Don't need this anymore. instead of other, we just use ourselves. Okay, let's see if it compiles. Well, we're not returning anything, so that would be an error, but oh my god. Oh wait, other.data. What am I talking about? No, this is cur. Wait. Oh my god, this is so confusing. By the way, my screen light just dimmed and before your eyes. I don't know if you saw that on the recording, but that's because I have the dimming turned on. We need to be doing this with cur, not other.data. Other.data of j. Right. Does that make sense? Yeah, because we index with, yeah, that's right. Right? It's not other.data of j, this is cur of other.data j. Yeah. Tricky. I'm not sure if that's right either. It's easier though just to write it and then see if it's right afterwards. So. Oh yeah, we never use that whole index because I forgot that we need to say cur of, oh wait a minute, is this, that's right, we need to, yeah, no, not cur, other dot data j, that's right, cur of whole index equals temp, like that. Surprising there are no errors because this doesn't return anything. Maybe it won't link. Oh no, you know what? Because we never even call this function, do we? Okay, so now after doing these, we're just going to return perm of names and cur like that. Now in here, we need to convert this into cycle representation. Oh, I don't want to do it. For now, let's just return star this and just print out that vector and see if it's right. Okay, so it compiled. It linked. Ooh, segfaults. Why? I don't want to step through in the debugger if I can help it. It's usually the best way, but it's also kind of painful. Yeah, let's debug it. And then I don't have TUI on this version of GDB. I don't even know how to get it. So it's going to be a little bit unpleasant. yeah, not main, not CDP. Duh. Yeah, there we go. Yeah. And run. Okay. It actually occurs to me that maybe it would have been better just to let it segfault and threads. What the heck? Who's making threads? Well, okay. Anyway, let's just go. Yeah, TUI is way better than this. But anyway, so stab. Oh yeah, okay. Finish. Stab. Next. Now let's look at what cur is. It should be 0 through. Maybe I can do this. Is that gonna work? Yeah, I didn't think so. Maybe standard cout. Yeah. I would like to know what's in there though. Error reading variable. Strange. Okay. So now we're at line 101 over here. I'm guessing we're gonna go to segfault like in one of these. Line 105. Huh, so far so good. Oh, there we go. Whole index. Why did that give a segfault? J equals -1. J should never equal -1. Oh, that's not true. Yeah, it'll quit at -1. Yeah. Oh wait, why is whole index -1 billion? Other.data of J cycles by. I bet you I can't look in it. Maybe what we need is some good old printf debugging. First, let's uncomment this. Oh, I took it out for some stupid reason. is correct. 0, 4, 0, 6, 8. So somehow in here, the whole index is getting set to some garbage value. If just in our heads we do, so cycles dot size is equal to 2, 2 minus 1 is 1, 1 is greater than 0. Cycles of 1, that's 4, minus 1 is 3. 0, 1, 2, 3. Temp is equal to 3, and the whole index right. Wait, yeah. No, the whole index is equal to 3. Let's try that again in the debugger. Seems reasonable. It's probably right. Now, don't know why it does that. That's kind of annoying. Oh wait, other data. Huh. Found the problem. Got it. Be wary of copy pasting code. I think we'll be okay now. Okay, so now we need to convert this into cycle representation, which is actually just done for us. Oh no, actually there could be some cycles there that I don't know about. Wait, no, hold on. This means 0 goes to 4, 4 goes to 2, 2 goes to 3, 3 goes to 5, 5 goes to 1, 1 goes to 0, 0 goes... Wait, no, that's not what it means. 0 goes to 4, 1 goes to 2, 2 goes to 3, 3 goes to 5, 4 goes to 1. Okay, so 1 and 4 are in a cycle. Wait, no. This is confusing. I need to write this function, or else I'm never going to understand if this is right or not. Okay, so here, I've written code to do this before. It's finicky. It's finicky as all hell. Thinking. Okay. Oops. Okay, so we're going to do cycles dot push back 0. Now, there's actually a reason to not use range-based iterators, because I actually need this index to check for, well, to check for elements that don't move, but also to detect cycles. So the way this algorithm works is basically exactly the way we do it by hand. It's just a challenge to get it written into the computer correctly. The way I did this by hand is I said A goes to D. Then I went over here to D. D goes to C. I went over here to C. C goes to H. H goes to E. E goes to B. B goes to A. We're done. Okay. So this is tricky, very tricky. You know what? I think what we need, vector of art n arrow n. It's actually kind of names. Yeah. And then we're going to do int pause equals 0 and int last equals 0. I might rename these variables. Give me a minute. I'm just trying to get this out so I can talk about it. Okay, we want to keep a vector of zeros and ones saying whether or not we've already treated this element. Well, this particular example has only one cycle in it. Let's say we had A, C, B, D, E. Let's say that that was our final permutation. Well, in this notation, where you just write it as a table of where stuff goes, it would look like this. A goes to C, B goes to D, C goes to A, D goes to E, and E goes to B. Okay. You know what? Why don't we work through an example that seems to help. So, let's put an F here. Let's put FGH. These are elements that don't move, so this should be an example of all the different types of things we could encounter. Okay. So at every iteration we perform the following. We find the first, no, wait a minute. Shoot. Let me think. Okay. Yes, okay, we don't just increase pause. No, wait. Here's the idea. Yeah. I'm thinking. We start pause at 0. First we check if this is a singleton, that is an element that doesn't move in the permutation. In this case, no, it's not. Because if it that would mean that it would be A here. A goes to A. The 0th element doesn't move, but that's not the case. It's a C. So we need to print out. Wait. We need to print out. This is really tricky. Really tricky. It's getting late. A, right? That's what it means. A goes to C. Okay, maybe this is the marked array. The first thing we do is we go here. Okay, we visited that. Then we go to the cth index. We mark it. Then we go to the 8th index. Oh, it's already marked. We have finished a cycle. We move on to D. We mark it. We go to the dth index. We mark it. We go to the eth index. We mark it. We go to the bth index. Oh, it's already marked where we finished a cycle. This is marked, but we haven't finished a cycle. We never started one. Marked, skip that. This is a singleton. Mark it, don't write anything. Mark it, don't write anything. Mark it, don't write anything. So the very first thing we need to print out is, no, at each time we print out pause. Yeah, okay, I got this. So int in cycle equals 0. We do if in cycle cycles dot push back yes. Yeah. Data dot size. And then we don't have to always query that. That calls a function. We just do int. Nah, let's just do that. It's cleaner. And this only gets called every once in a blue moon, so who cares? Now, when we don't do this, we just push back pause. Then we do pause equals, and we do in cycle equals 1. Does that make sense? Does it compile? It compiles. So here, let's not return star this. Let's return perm of names and cur, just like that. this out. All right, let's see how we did. Probably a seg fault if I had to guess. Yep. So, okay, let's go through this. Cycles that pushback 0, that makes sense. It cycles 0, well, pause is less than name 0n. If v of pause is equal to pause, that's not the case. So we increase pause. If that, but that was not the case, so that doesn't happen. If pause is marked, oh, let me check the constructor for vector to see how to initialize stuff too. Actually, did I mark anything? Yeah, I should mark stuff. We're probably still going to get a seg fault. Yeah. So, well, pause is less than name 0n, which is equal to 1, 2, 3, 4, 5, 6. It's not marked, so we mark this position. We push back 4 into data. And then we go pause is equal to v of pause. 0, 1, 2, 3, 4. So pause goes here. And we set end cycle to 1. We go back. Is it equal to itself? No. Is it marked? No. We mark it. We push back pause. Now we have 4, 1. Now we go to index 1. No, no, mark it, push it, go to index 2. No, no, mark it, push it, go to index 3. No, no, mark it, push it, go to index 5. No, no, mark it, push it, go to index 0. No, yes. And we are in a cycle, so we push back data.size and cycles. And then we do, I see the problem. These are all mutually exclusive, or should be. Okay, I feel pretty good about that. Add Cheb, we did it. We did it. Okay, great. Awesome, awesome. Now I want to get rid of that because we don't need that anymore. And let's take it for a test drive. What else did I leave in? Get rid of that. Add Cheb. Yeah, look at that. Yeah, pretty good, pretty good. So let's open up Gap and try some stuff. So let's change these to be Okay, so A times B should be 1574286. Look at that, not too shabby. Now let's do, let's see if that breaks anything. Or actually, even more interesting, P1 times P2. And then let's do P3 equals P3 times P3. That looks right. 1726548. Oh yeah, right. Is that, yeah. 1258764. Not bad. Let's try A, B, B, A. Okay, these are more interesting. A times B. So the first one is A times B times B. 186.35742. Oh, mine doesn't order them. That's a problem. Mine should order them, because otherwise it's a lot harder to check for equality, which we need to do. Why doesn't it? It should. It should. Why doesn't it? I don't need this here, obviously, but I'll put it anyway because it makes sense. Okay. Fascinating. It sorts them by order of first appearance in the strings. It doesn't sort them by string comparison. So the options are keep a sorted namespace, or to sort the permutations as we construct them. I'm going to go for the second one. To sort the permutations as we construct them. Now, the way to do this is to, for each cycle, find the minimum, and then rotate this cycle until the minimum is on the left-hand side. So let's do it the quick way using the algorithm header. Now the min doesn't return an iterator, it just returns, oh wait, min element. I don't think it returns an iterator. Oh, no, it does. And then what does rotate need? Oh, perfect, it takes iterators. Yeah, perfect. This should be a cinch. Should. Okay, for each cycle, so think it's going to work on the first try. Those two compiles. Nope, didn't work. Did not work. Oh, yes, that's right. Shoot. We need to convert them to the strings. We need to convert them to the strings. Oh, wait a minute. No, we don't. Because the internal integers are sorted, and that's all we need to perform comparisons. The only reason to sort them by the string representation is to make it nicer for the user to look at. So we might still do that. But actually, this autosort has no benefit. It doesn't do anything. It literally doesn't do anything. It never will, because things are already sorted. So I'm going to get rid of it, despite how easy it was to write. Okay. So actually, the only thing we might change is the printing operator. I'm not even sure I want to. Yeah, don't want to. Okay, so now we have the multiplication, which is working. Now I'd like to do No, I don't want to do this right now. I don't want to, I was going to write a function to look up a name, but I don't want to do that right now. So this operator is what applies permutation to an element. So I'm getting quiet and not explaining what's going on. So normally what you would do is this isn't it. Let's say I wanted to ask, where does 2 go when I apply this permutation to it? I would go and find 2 and look at the next one. Problem, if the next one is the beginning of a new cycle, I actually have to go back to the beginning of this cycle and get that element. So that's the annoying bit here. I don't really know a good way to get around it. Kind of makes me think that using this representation internally may not be as good as the representation that is naturally used by as in this table representation here, because then it would just be a straight lookup. It'd be super easy. What would permutation multiplication look like? Oh, that would be easy as well. You would just, well, apply what this means, as in take the 8th element and put it where C is. Take the bth element, put it where D is, and so on. Or that's not what it means. I said that wrong. Let's say we were applying it to the numbers 1, 2, 3, 4, 5, 6, 7, 8. This means take the number 1, put it at location C. Then this means take the number 2, put it at location D, right? So we've got 1, 2 here like that. You'd have to hold on to the old vector. You would do this in a new vector. So take the number 3, put it at location A. Take the number 4, put it at location E. Take the number 6, put it at location F. I seem to have made a mistake, but you get the point. Oh yeah, I skipped over the 5. So that's, you just straight basically copy it to a new vector. I was a little bit too anxious to use Donald Knuth's fancy schmancy one. Should I change it? Or should I add this other representation in and keep them both? Well, how does gap do it? How do I find out how gap does it? Yeah, that's how they do it. I mean, if gap does it that way, it's for a good reason. So they say the trade-off here is that if the largest number you have is a billion, then there's going to be a billion things long. So I don't have to do that. Well, that's not completely true though, is it? Oh no, no, that's okay. Yeah, but I think that this is probably fine. Okay, let's leave it the way it is. Now that I know that there's a trade-off, then in some sense it's worth it to try the other one just to see if it's better at all. Okay. Okay, let's test it. Oh man. Excuse me. Maybe it's order of operations. Oh yeah, okay. 2 does not go to 7. Darn. 2 does not go to 7. Oh, no. Right. I was tricked. Yep. That's the internal number. So there's a really clever hack I'd like to perform now in that case. I'm going to force them to be equal to their internal representations. 2 doesn't go to 4. Oh my god. Let's see what's going on. Ooh, okay. have problems. 1 goes to 6. 2 apparently goes to 4, which is wrong. 3 goes to some ridiculous number. Why? And we got a seg fault. What the heck? Aha, that was dumb. Must be getting a little too tired for this now. That's better. 1 goes to 6, 2 goes to 8, 3 goes to 7, 4 goes to 5, 5 goes to 4, 2 goes to 8. Wait. 1 goes to 6, 2 goes to 8, 3 goes to 7, 4 goes to 5, 5 goes to 4, 6 goes to 2, 7. No, 6 goes to 3, 7 goes to 2, 8 goes to 1. Okay, we're in business. We're in business. So we did that. I think that is probably a good time to end, although I have a very strong temptation to keep going because the ultimate goal of this program is to be a Rubik's Cube solver. And there are yet more things to try, but it's too late to get into it. Okay, well, that's it.